Our final topic of electric and magnetic fields is the motion of charged particles in magnetic fields, and in this slide presentation in particular we'll be looking at the forces on charged particles in magnetic fields. Previously we have seen current carrying wire experiences a force when it's placed in a magnetic field. Now, as current is the flow of charge, we can assume that a moving charge can also experience a force in a magnetic field. There are a number of factors that affect the force of a charged particle in a magnetic field. They are the state of motion of the particle, meaning if the particle is at rest and not moving, there is no magnetic field associated with that particle, and the external magnetic field does not influence that particle. Another factor is the magnitude and direction of the velocity of the moving charged particle, the magnitude and sign of the particle, and the magnetic field strength itself. The magnitude of an electric current is defined as the rate of flow of electric charge, and this is given by the equation I equals delta Q on delta T. An example, if only one electron moves past a point in 1 second, then the average current in the circuit, or through that point, during that second will be theoretically the charge of an electron in amps, as the charge is the charge on an electron and the time is 1 second. So I've got this image here where an electron is moving along a wire, for example, and you can see the path of the electron is left to right. Now, in physics, when we're talking about conventional currents, we're actually talking about the direction a positive particle might move. This dates back a couple of hundred years to when this concept was first discussed and before electrons were discovered. So we're talking about a conventional current going in the opposite direction as the electrons. So you might see this in this diagram down here, and we're looking at a positive and negative terminal, say on a battery, and you might see this in a circuit. So what this means is that the positive, or the conventional current, flows from the positive to the negative, and you can think of this as electrons, which are negative, leave the negative terminal. So the electrons will be going right or left to right, and the positive charges might leave the positive terminal, so they travel right to left. Electric current doesn't need to be the flow of electrons in wire. Any flow of electric charge in any medium can constitute a current. So I've got a few examples here. In the bottom right I've got lightning, which is the flow of charge in the atmosphere. In the red picture I've got two wires with spark going between them, and that's also the flow of charge in the air or atmosphere. And in the other diagram I've got a battery, which we can have a look where the flow of charge is actually in the solution, and it's going from the anode, which is on the right, to the cathode, which is on the left, with the electrons going right to left. As the electrons are going right to left, this means the conventional current is in the opposite direction, so meaning the conventional current is left to right. We have looked at the force on a unit current element in a magnetic field. So if we had a charged particle Q moving at a speed v at an angle theta to the field B, we can find the force on it by the equation that's written on this page. If we look at an example though, where we don't have the unit current element, rather we have a charged particle that's moving through our magnetic field, how do we define the current element that's associated with that charge? Let's consider the moving charged particle for t seconds through the magnetic field. The average current passing at any point in the path is found by the charge over the change in time, and this is one component of the current element that we discussed earlier. Also, in t seconds, the charges move the distance of v naught t, where the v naught is the speed of the object and t is the time. So this is found in our range equation for projectile motion. This relates to the distance or the length of the current element, delta L. So what we can do is we can put these two equations together and find an expression of the force on the particle in a magnetic field. So substituting the previous two equations into our original force equation which is this one, we can substitute the values for current and the value for length, and we get our final equation of F equals QVB sine theta, where now we're looking at the charge of the particle, the velocity, and the magnetic field strength. From this, we can see that if the particle is stationary, there is no magnetic force, as V will equal 0. If the particle is moving parallel or anti-parallel, there is no magnetic force, as theta will also equal 0. So that's when the particle is moving in the same direction, either left or right, to the magnetic field lines. We can also see the maximum force is when the particle is at right angles to the field. So that's when theta is 90. So that's when we've got the particle traveling up and down compared to this particular magnetic field. We can also see the greater the speed, the greater the force. So the faster the charge is, the greater the force occurs. We can also use the right-hand palm rule to determine the direction of the force on the charged particle due to the magnetic field. So as a reminder, we've got our fingers that point in the direction of the magnetic field. Our thumb points in the direction of the positive flow of charge. So for example, if we had an electron, our thumb will point in the opposite direction, and our palm points in the direction of the force. Now what we have to remember though, is that if the charge is moving at any angle in the field, our thumb points in the direction of the component that is perpendicular to the field. So for example, if we take this picture here and we take this charge, let's just for this example call it a positive charge. Okay, so one component is perpendicular to the field and one component is parallel to the field. Now we're only interested in the one that is perpendicular, which is pointing up. So to determine the direction, let's point our thumb up. Now our fingers will go in the direction of the field, and then we can see that our palm is facing away from us, meaning the force is into the page.